Good morning to all of my students. Myself, Mr. Dibyendu Mondal, Assistant Professor of Mechanical Engineering Department of Greater Kolkata College of Engineering and Management under GIS Group. In this pandemic situation, I am delivering my lecture through online mode and my video is uploaded in YouTube.
Good morning. Today I am discussing about solar dryer. Actually, the drying process removes the moisture and helps in the preservation of any product. Solar crop drying is perhaps the most ancient and widespread direct use of solar energy. The customary way to spread the material to be dried in a thin layer on the ground. The disadvantages associated with this method are the process is slow, the product is vulnerable to attack by insects, and dust gets mixed with the product. The use of solar dryer helps eliminate these disadvantages. Also, drying may be made a faster and controlled process and better quality product can be produced. A simple cabinet type solar dryer is shown here. It is an enclosure with transparent cover similar to a greenhouse. The material to be dried is placed on perforated trays. Solar radiation enters the enclosure and is absorbed by the product as well as the surrounding internal surface of the enclosure, increasing its temperature. Here the diagram is given. Solar cabinet dryer, one line that is the solar radiation, and another one is the product on perforated trays, cabinet, air out, transparent cover. So the inside air heats up to a temperature ranging from 50 to 80 degrees centigrade and rises above natural circulation of air is ensured by providing suitable opening at the bottom and top. The circulating air removes the moisture from the product. For large scale drying, forced circulation of air may be used by employing a blower. In case of green lumber, where direct exposure to the sun tends to produce curling and wrapping, or for products where direct sunlight is not adequate, controlled temperature drying known as kiln drying may be used. Here, the air is heated separately in an array of solar air heaters and then ducted to the chamber where the product to be dried is stored. Such dryers are also suitable for food grains and food products like tea and tobacco. Next one is the solar distillation or dissolution of water. Actually, potable or fresh water with less than 500 ppm parts per million salt content is one of the fundamental necessities of life for humans. Industries and agriculture also require fresh water, without which they cannot thrive. Humankind has been dependent on rivers, lakes, and underground water reservoirs to fulfill his need of fresh water, an act that is intimately associated with the evolution of civilization. Because of rapid industrialization and the population explosion, the demand of fresh water has increased enormously with the rise in the standard of living. The average per capita assumption consumption of water has also increased. Due to climate changes and less rainfall in many parts of the world, fresh water, which was available in abundance from rivers, lakes, and ponds, is become scarce. Also, the available resources are getting polluted due to discharge of industrial effluents, and sewage in large quantities. Thus, due to climate change, pollution and overconsumption at present, more than 2000 million people have no regular access to adequate safe water. In most villages, people travel up to 30 km to collect fresh water. According to one estimate, about 79% of water available on the earth is salty and 20% is brackish, means less salty water from wells, and only 1% is fresh. Therefore, conversion of brackish or saline water to fresh water through the distillation process using solar energy is a good idea where plenty of saline water and sun are available. The use of solar energy for distilling, desalting seawater and brackish well water has been demonstrated in several moderate sized pilot plants in the United States, Greece, Australia, and several other countries. The idea was first applied in 1872 at Las Salinas, Chile, in a plant supplying drinking water for animals, working in nitrogen mining areas for transport. The conversion device is known as solar steel. Model development in solar radiation have been directed to use of material and design for economic and durable construction with increased output in order to reduce the product cost. Several types of solar steel have evolved. However, only the basin type has been tried commercially on a large scale. A simple basin type solar steel consists of a shallow blackened basin filled with saline or brackish water to be distilled. The depth of water kept about 5 to 10 centimeter. It is covered with a sloppery transparent roof. Solar radiation after passing through the roof is absorbed. Solar radiation in passing through roof is absorbed day by day increasing. The condensed water slips down the slope and is collected through the condensate channel attached to the glass. The evaporated water increases the moisture content. This is the diagram. Actually, simple basin type solar steel, saline water, solar radiation, and condensed water drops, black button, condensate channel, and distilled water. Okay, this is the simple basin of basin type solar steel, saline water goes like that. The steel is created in an open area with its long axis facing the east-west direction. The steel can be fed with saline water either continuously or intermittently. The supply is generally kept at twice the rate at which the fresh water is produced, but may vary depending on initial salinity of input water. The output of a typical solar steel in Indian climate varies 5.31 per 5.3 liter per meter square. Actually, solar thermomechanical system. It is possible to convert solar thermal energy to mechanical energy through heat engine using Rankine cycle, Stirling cycle or Breton cycle. The mechanical energy thus produced may be used for application requiring shaft power such as water lifting, cooling, etc., or may be converted to electrical energy using an alternator. Effective conversion of solar thermal energy to mechanical energy is associated with many limitations. The efficiency of a collector system decreases as the collection temperature increases, while the efficiency of a heat engine increases as the working fluid temperature increases. The conversion efficiency is low. A part of thermal energy is lost during the transportation of the working fluid from the collector to the heat engine. Solar collectors are generally more expensive than engines. A very large area is required to install the solar collector system. Due to the intermittent nature of solar energy, storage of thermal energy is also required, which has its own problem like degradation of storage material, degradation of storage material with time. So solar thermal water pump. Some features of solar energy makes its utilization attractive for irrigation water pumping. These are the more irrigation water is required in summer when solar energy is available most. Intermittent pumping is tolerable and can serve the purpose. Surplus energy can provide pumped storage in the form of a pond. Several solar irrigation pumps have recently been tested in many countries. While in the lower range 200 watt to 5 kilowatt, solar photovoltaic pumps are more successful in higher ratings. Solar thermal pumps. A schematic diagram of typical Rankine cycle solar thermal water pump is shown. A solar collector system may consist of flat plate collectors, non-focusing type, collectors or sun tracking concentrator. Water is used as a heat transport fluid, yields its heat to a low boiling point organic working fluid in a heat exchanger. Surplus heat is stored in the thermal storage to be used later when the sun is not available. The high pressure vapors of the working fluid expand in the turbine, condense in the condenser and returns in the heat exchanger. A part of the irrigation pumped water is diverted through the condenser for cooling purposes. So this is the diagram. Solar thermal water pump, thermal storage and solar collector, hot water in, and then with the help of heat exchanger, freon vapor go to the turbine to condenser, and another one is the irrigation well, water for irrigation, solar vapor compression for irrigation, solar cooling compression for irrigation. Okay, cooling system based on the vapor compression principle has the advantage that the system apart from cooling can also be used in a heat pump mode. In the cooling mode, the system absorbs heat from space to be cooled and delivers it to the ambient, which is at higher temperature. Whereas in a heat pump mode, the system absorbs heat from the ambient and delivers it to a space, which is at a higher temperature. A solar power based vapor compressor cooling system is shown here. A solar vapor compression irrigation system, solar collector, this one is the hot water, heat exchanger, Rankine loop, condenser, heat exchanger, evaporator from to space to be cooled, okay, freon liquid, okay. This one here, solar power is first converted to mechanical power in the same explained above. So solar vapor compression refrigeration system, this is the schematic sketch. Okay, here solar power is first converted to mechanical power. Same explain, the shaft power thus produced drive the compressor of a conventional vapor compression refrigerator. A suitable refrigerant vapor is compressed and then condensed to a liquid, rejecting heat to the ambient. Now the pressure is reduced by passing through an expansion value where it gets evaporated. From the space to be cooled and reject it in the condenser. Now, solar pond electrical power plant. A solar pond electrical power plant shown here. A non-convective solar pond serves the purpose of a large flat collector as well as long-term thermal storage and can provide sufficient heat for the year. Now, black bottom serves as an absorber and the layer of still water above it is used as an insulator rather than normal glazing and air space. In a large area pond approximately 1 to 2 meter deep, a vertical gradient of salt concentration is maintained such that most concentrated and dense solution are at the bottom. The salt concentration varies from 20 to 30% at the bottom to almost zero at the top. Left to itself, the salt concentration gradient will disappear over a period of time because of an upward test. Okay, because of an upward this one. The amount of salt required for this purpose 50 gram per meter square per day, which is a large quantity. Now, because of movement of mixing of fluid at the top at the bottom, the solar pond is characterized by three zones. One is the surface convective zone, non-convective concentration zone, gradient zone, and a lower convective zone. The surface convective zone usually has a small thickness around 10 to 20 centimeter. It has uniform temperature close to ambient air temperature and low uniform concentration close to zero. The non-convective zone is much thicker and occupies more than half the depth of the pond. In this zone, both temperature as well as concentration increase the with depth. It principally serves as an insulating layer and reduces heat loss in the upward direction. It also serves as a part of heat storage as some of the heat collection takes place in this zone also. The lower convective zone is comparable in thickness to the non-convective zone. Both the temperature and concentration are nearly constant in this zone. Solar radiation penetrates through water up to a blackened bottom where it gets absorbed and increases the temperature near the bottom. In spite of the temperature rise of the bottom layer of the brine, its specific gravity remains higher than that at the top because of the concentration gradient, and thus convection mixing is minimized. Okay, the hot brine from the bottom is slowly withdrawn. These values are lower than those obtained for a flat plate collector. Nevertheless, solar ponds are most cost effective since their cost per square meter is much less than that for a liquid flat plate collector. Okay.
Last, if you like my video, you have to subscribe. Okay.